Hello everybody and welcome to Thermal Physics Lesson 7. Now in the last video we looked at Maxwell-Boltzmann distribution, we looked at RMS velocity and we looked at velocity in 3 dimensions. Now just to bring forward the salient points really from the last video, firstly if we have a look at RMS velocity and remind ourselves about RMS velocity, we'll remember RMS we just work through backwards, so we take all of our values and we square them. V4 squared all the way up to the nth, so capital N for the number of molecules. We then take the mean of those, so of course to take the mean we add them all together and we divide by the number we've got, and then finally we square root. And then obviously for 3D velocity we said the total velocity squared is the square of the individual components, Vy squared plus Vz squared, or of course if you square root through, get rid of that squared and we can square root all of that. Now it's important that we get those ideas back into our minds at the start of this video because we are going to be revisiting those during this video. Now as I said in the last video, what we've got in these couple of videos is a little mini series within the topic on kinetic theory. And obviously, as you can tell from the title, the final aim of what we're going to be looking at in this video is getting an equation for kinetic energy and linking that to temperature. Firstly though, we're going to take a slightly different approach. We're actually first going to look at pressure. And the sort of end aim of what we're looking at, the end goal, is to look at pressure for all molecules in a gas, so n molecules, and obviously looking in all 3 dimensions. Okay, so that is our target. But of course, in order to get there, we're going to try and break this down into stages. So instead of going straight for n molecules and 3 dimensions, firstly, we're going to look at 1 molecule in 1 dimension. We'll then scale that up to n molecules still in 1 dimension, and then finally we can get our target, which is n molecules in 3 dimensions. Now of course, in order to calculate pressure we need to do force over area, and in order to calculate force we're going to take Newton's second law properly and work out the rate of change of momentum. Now note that we've got the letter P twice in here, but unfortunately they mean 2 different things. So this one is pressure and this one here is momentum. So as I'm going through this derivation, just keep that in mind and make sure that you understand whether it's P for pressure or P for momentum that we're looking at. Now, in order to look at 1 molecule in 1 dimension, let's take our molecule here and let's say that it's moving in this direction with a velocity of Vx. So let's define that as the x dimension, that as the y, and that as the z. And therefore, at first, we're just going to look at the pressure that 1 molecule puts on that wall, that one particular wall that I've shaded in blue of the container. So let's have a look at the pressure of this molecule then. So we know full well, so let's just remind ourselves we need force over area, but of course force is the rate of change of momentum. So first let's have a look at what the change in momentum of this molecule is going to be. So here's the wall then, here's our molecule, and our initial idea, our before collision, is that this molecule is moving the way that we've drawn it to the right. Now the momentum at that point is going to be the mass of the molecule, which is going to call m, multiplied by the velocity vx. After the collision then, the molecule is going to be moving back in the opposite direction to the left. Now the mass obviously remains the same, but because we've changed direction, we now need to put a minus sign in there with the velocity. Now obviously the minus sign just shows us that we are changing direction. Now of course, how do we know that at least the magnitude of the velocity is going to stay the same? So how do we know that we're going to have mvx from momentum going in and we're going to have the same magnitude of momentum coming out? Well, of course, this goes back to the assumptions that we made in the last video. And assumption number 4, if you remember back and maybe go back, is that all collisions are elastic. In other words, no kinetic energy is lost. So make it a note at that point. So EK is conserved. Okay, now you might want to go away and convince yourself that if we're conserving kinetic energy, obviously we're conserving mass, and therefore we've got to conserve at least the magnitude of the velocity at the same time as well. So both of those molecules will have the same kinetic energy before and after. Now, of course, in order to calculate change in momentum, we always do final minus initial. So our change in momentum will now become this. Well, the final is what I've written as after, so it's minus mvx minus the initial, which of course is mvx. So the change in momentum then, when we calculate that through, so minus mvx minus mvx gives us a total of minus 2 mvx, and there is the change in momentum. So that bit there is done. Next thing we need to do then is calculate the time. Now for the time, what we need, okay, is we need the time between successive collisions with the same wall. Okay, so again, remember that one of our assumptions that we made in the last video, which is number 5, if you remember back, is that the collisions take negligible time compared to the time between the successive collisions. So it's the time between successive collisions that we need for the delta T here. So in other words, we need the time that it takes for the molecule to collide with this wall, to go all the way over to the other wall, and then come back and collide with the same wall again. Now, of course, in order to do that, we're just going to use the old classic of speed equals distance over time. So the time is going to be the distance over the speed. Okay, and the distance here, well, because it's going from the blue shaded wall all the way to the other side and back again, the total distance there works out as 2x. And we've got the speed already. We know that that speed is vx by definition. Let's tie both of these together then to at least calculate the force before we move on to a new slide. So we know that force is rate of change of momentum. Okay, so we've got the change of momentum, which is minus 2mvx. We've also got the time now, which is 2x over vx. Now, of course, in order to tidy that up, on the bottom we've got divided by Vx, so that ends up on the top. And you'll also notice that the 2's cancel out as well. So the final idea then that we've got is m Vx squared over x. Let's now bring that forward to a new slide then, so that's just bringing everything forward from last time. So f is equal to minus Vx squared over x. Now at that point, hopefully you may already be thinking to yourself, well, we're looking at kinetic theory, we obviously need kinetic energy in some way, shape or form, and we've already got on the top of this equation mv squared in some way, shape or form. So hopefully already we can start to see that we're getting the idea of kinetic energy already sort of subtly starting to appear in our equations. But anyway, we still need to get the pressure of this one molecule in one dimension. Now, at this point, I want you just to think back to maybe what we did on the last slide. When we drill down into it, when we look at it properly, this force that we've just calculated is the force that acts on the molecule. Okay, because obviously the molecule has gone from moving in that direction to moving in that direction. Therefore, in order to change the direction from right to left, the way that we've drawn it, there must be a force acting to the left. Now, of course, when we're looking at pressure, we're not really interested in the force on the molecule. What we need is the force on the wall. And therefore, by Newton's third law, which of course states that for every action there is a reaction of equal magnitude and opposite direction, what we end up with is the force on the wall has the same magnitude F but opposite direction. Okay, so the force on the wall has the same magnitude but opposite direction. Okay, therefore the force on the wall becomes the negative of the force on the molecule, but of course negative and negative cancel each other out, and the force acting on the wall therefore becomes Vx squared over x. Now, of course, the final stage we're still looking for pressure, and remember that pressure is equal to force over area. So we've got the force, we've got mVx squared over x, and we now need to divide that by the area. Well, again, going back to the diagram in the top left, you can see that the area is y times z. So the area is yz. Now, again, tidying all that up, we end up with mvx squared over x, y, z. And of course, finally, what we spot is that x, y, z on the bottom, well, they are just the three dimensions of the container, this theoretical container that we've come up with. And therefore, when we multiply the three different dimensions together, we just end up with volume. And therefore, finally, we have the pressure of one molecule in one direction, which is obviously the x dimension, in this case, ends up as m Vx squared over the volume. Now, interestingly, at this point, and just sort of taking a bit of an aside at this point, if we multiply both sides by the volume, we end up with pressure, at least in one dimension, times the volume is mVx squared. Now, of course, if you remember back to when we did the gas laws, we said that the unit of this left-hand side is joules. In other words, the pressure times the volume is a measure of energy. And of course, with very little to think about, we can see as well that the right hand side of this, mv squared, is going to have the unit of joules as well. Of course, we know that kinetic energy has the half in there, but of course the half is dimensionless, so we know that energy is in joules, the half is dimensionless, so therefore m times v squared must also be in joules as well. So hopefully that just ties that back to a couple of lessons ago, a couple of videos ago, when I made that statement that P times V has the unit of joules as well. The next stage then is to take our pressure in one dimension and now sort of scale this up to look at all of the molecules, so to look at n molecules. Well, of course, the pressure from n molecules is just going to take all the individual molecules and we're just going to add them together. So the total pressure will be m Vx squared over V for molecule 1. And we'll add to that mVx squared over V for molecule 2, plus obviously all the other ones all the way up to mVx squared over V for the nth molecule. Now, assuming that all the molecules in the gas are exactly the same, therefore have the same mass, we know that they're in the same container, so the volume is the same. And you can see that therefore every single term has got mass divided by volume, so therefore we can factorise that out. So we end up with m over v, and then we just have, so Vx squared for molecule 1 plus Vx squared for molecule 2 all the way up to Vx squared for molecule n. Now, hopefully the bit inside the brackets looks familiar to you, and this is why I made the point of revising the RMS velocity at the start of the video. So remember that VRMS is equal to root of V1 squared plus V2 squared plus V3 squared all the way up to Vn squared over n. So what we've got inside the brackets here is just the top line in this VRMS bit. So in other words, if we rearrange that, we can do a little bit of substitution here. So obviously the first thing we're going to do is we're going to square. So VRMS squared is equal to V1 squared all the way up to Vn squared over n. And then obviously we're going to, sorry, I've put an extra squared in there. We're obviously then going to multiply both sides by n. So n times the RMS squared is equal to V1 squared plus all the way up to Vn squared. And therefore, instead of this, what looks at the moment like quite a horrible brackets with loads of terms in, we can reduce that down very simply to n V RMS squared. So let's do that. There's our n for the number of molecules, there's the mass of an individual molecule. We then need the RMS squared. I'm just going to put the x there to remind us that this is only in one dimension at the moment, and obviously we're going to divide that by the volume. So there you go, there's our next term, the next stage. We've now got the idea of the pressure from all the molecules, but of course only at the moment moving in one dimension. Now, of course, what we could do if we wanted to look at all the different dimensions to look at the molecules moving in the y direction and molecules moving in the z direction. We could go all the way back to the start and repeat all of this, but hopefully you can see that we're going to end up with the same answer every time. So while this is the pressure in the x direction, the pressure in the y direction will just be V RMS squared in the y dimension over V, and of course in the z direction we've got N V RMS squared in the z direction. So we're into the final stretch with pressure now. We've got an equation for n molecules in one dimension. We just now need to scale this up into the 3 dimensions. So let me just remind you of how we go to 3 dimensions from last video and the start of this video. Total velocity is Vx squared plus Vy squared plus Vz squared. Now, of course, while that works for one molecule with 3 different components, it also works when we're looking at RMS as well. So we can say that the VRMS is equal to the RMS in the x direction squared plus the RMS in the y direction squared plus the RMS in the z direction squared. Now it's at this point that we need to make sure that we understand the concept, okay? And this actually goes back to the 3rd assumption that we made in the last video, which is Brownian motion. Now, one of the ideas in Brownian motion is that the characteristic velocities, the characteristic speeds of the molecules in all 3 dimensions will be the same. And what that means is that the RMSs in the 3 different directions will also be the same. So Brownian motion tells us that Vx will be equal to Vy. Sorry, it's the RMS we're looking for. So VRMS in the x direction will be equal to the RMS in the y direction, which will be equal to the RMS in the z direction. Now, just to kind of sort of get that idea into your minds and really justify that idea into your minds, we obviously know that we're going up and we're going to look at energy in a moment. So we're going to look at how that links to temperature, and we are going to get an equation that finally links these ideas together after 6.5 videos of me saying that temperature and energy are linked. Now, we know that if we were to take a temperature probe and take a sort of a thermally isolated room and look at it, no matter which direction we point our temperature probe, our thermometer in, we're going to get the same temperature, because it comes down to energy, and obviously energy is a scalar and direction doesn't matter when we're talking about scalars. So therefore the characteristic velocities, in other words the RMS velocities, in all 3 dimensions must be the same. If they weren't the same, we'd have different energies in different directions, which suddenly puts an energy factor, a direction factor into the energy, which of course doesn't make sense with energy being a scalar. Okay, so we have to have those 3 RMSs in the 3 different directions being the same. Now, therefore, when we substitute all of this in, remembering that VRMS in the y direction is equal to VRMS in the x direction, so we're going to substitute that into there, and of course it's the same as it is in the z direction. We're going to substitute it into there. What we've got on the right hand side of that equation is 3 of exactly the same thing. So we end up with VRMS squared is equal to VRMS in the x direction squared, plus, well, with the substitution, VRMS in the x direction squared, Okay, so that's substituting in for y, because of course those two things are equal, plus v squared for the RMS in the z direction. So there is the other substitution in. Sorry, it's not z, of course. It is x. So we've got 3 of exactly the same thing. If we divide both sides of this equation by 3, then we can see that v squared of the RMS in the x direction is a third of the RMS in all 3 dimensions, a third of the total RMS squared. So when we substitute that into our pressure equation, what we're left with is that the total pressure is equal to, well, Nm multiplied by a third of the RMS squared over V. And then when we tidy that up, I'm going to multiply both sides by V, and we're left with P times V is equal to a third Nm times the RMS squared. And there finally then is our equation for the pressure of n molecules in 3 dimensions. Now, of course, finally, it wouldn't be kinetic theory if we didn't at least have a look at kinetic energy. And as you said all the way through, and obviously I mentioned a couple of slides ago, remember that P times V has the unit of joules. So we're actually already most of the way to getting the equation for energy that we need. Now, of course, you might have already have guessed the reason why I've rearranged it to make it P times V on the left-hand side is to make this look like the ideal gas law. So remember the ideal gas law, PV equals nRT, or PV is equal to nKBT. Now, of course, what we could do is we could take that third NMV RMS squared and we can equate it to either nRT or nKBT. Now, of course, the easier one to do here would be the second one, would be the N times Boltzmann's constant, capital N times Boltzmann's constant times the temperature, because straight away the capital N's for the number of molecules is going to cancel itself out. But what I'm going to do, I'm actually going to do it the other way around. I'm going to do it the more awkward way, just to really take an opportunity to remind you how all of the constants work together. And then obviously I'll show you the easy way anyway. So here we go, then let's do it the more difficult way first. So NMV RMS squared is equal to nRT. Now, of course, the first thing that I want to do is I want to divide both sides by the number of molecules. So we end up with a third mv RMS squared is equal to n R over the number of molecules times the temperature. Now, at this point, we just need to remember, as I said, how all of these constants relate to each other. So first you remember that the number of moles is the number of molecules divided by Avogadro's number, and therefore little n divided by big N, so the number of moles divided by the number of molecules, leaves us with 1 over Avogadro's number. And therefore this term here, little n r over big N, so little n r over big N now becomes r over Avogadro's number, which of course by definition is Boltzmann's constant. So we end up with a third mv RMS squared is equal to Boltzmann's constant times the temperature. Now, of course, what we could have done and taken the easier way, I'll just show you the easier way as well. So v RMS squared is equal to n kBt. Well, of course, if we'd have done that, where you can see that we've got the number of molecules on both sides, which cancels out and leaves us with a third mv RMS squared is equal to kBt, as we had before. So like I said, I'll just show you the more complicated version just to remind you about how all of these constants work together and sort of redefine each other. But of course, we can still take the easy option as well. What we're left with then, so let's just bring this back up here, a third mv RMS squared is equal to kBt. Now, we've said that we want kinetic energy, so on the left hand side we want a half mv squared, but what we've got at the moment is a third mv squared. So we just need to do a little bit of multiplication and division to work through to get the right thing. Well, firstly, let's get rid of the factor of a third, so let's multiply both sides by 3. Okay, so what we're left with is mv RMS squared is equal to 3 kBt. And then finally, we just need to divide by 2 or multiply by a half, and we're left with a half mv RMS squared is equal to 3 over 2 times Boltzmann's constant times the temperature. Now, of course, we can see that we're pretty much there with kinetic energy. We've got half mv squared on the left hand side of the equation, but it's not mv squared, it's not v for just one molecule. Of course, when we're talking about RMS, this gives us the idea of some kind of mean for the velocities. So of course what this means, excuse the pun, is that this kinetic energy is what we call the mean kinetic energy of the molecules. And therefore, finally, we can say that the mean kinetic energy, Ek bar, remembering that the bar is used obviously in maths and in physics to represent the mean, is 3 over 2 times Boltzmann's constant times the temperature. And therefore, finally then, you can see that, again, like I said, I've been promising this for a few videos now, we've finally got an equation that links kinetic energy with temperature. Rather than having a question then associated with this video, as we've already gone over the half an hour mark, we might as well move straight on to the summary. Now, I understand that this video has been very theory heavy. It has been very derivation heavy. What I suggest you do is maybe go over it a couple more times and just really make sure that you've got in your mind exactly what's going on here and exactly how we've calculated everything. Now, the two sort of key things that we need to get out of this video then are pressure. So remember that the pressure times the volume is a third nmv RMS squared, and that represents the pressure of n molecules in 3 dimensions. And then finally, the kinetic energy, or the mean kinetic energy of a gas, is equal to 3 over 2 times Boltzmann's constant times the temperature. So that's it for this video. As I said before, I suggest with this one that you go over it maybe a couple of times to really get that knowledge into your head and make sure that you fully understand what we've gone through in this video. And of course, as usual, thanks for watching, and I'll see you next time.